a cochlear implant. So it's a review by non-Cochlear. Yeah.
Think about sound for a moment. Just how fundamental it is, right? It's how we connect, how we experience so much of the world.
Absolutely. But what happens when that experience changes? Maybe drastically. When you rely on, well, some pretty amazing technology just to access the world of sound.
That's exactly where we're going today. We're diving deep into cochlear implants, or CIs.
And not just the basics. We're looking at how the tech is evolving, how it's sharpening speech understanding, yes, but also something maybe less expected, music enjoyment for people using CIs.
Okay, right. So for this deep dive, we're leaning on some recent, really interesting research papers.
Yeah, these aren't just dry lab reports. So they get into the nitty-gritty of signal processing, sure, but also user-focused design and really the human side of hearing with an implant.
And our mission, like always, is to pull out those key insights for you, give you a shortcut, maybe spark some of those aha moments without you having to wade through all the dense material yourself.
So starting point, what is a cochlear implant? At its heart, it's this incredible bridge to sound.
A bridge. I like that.
Yeah. It takes acoustic wave sound and converts them into electrical signals. These signals then directly stimulate the auditory nerve fibers. It's a way to bypass the damaged parts of the inner ear.
And the way it mimics natural hearing is, well, it's pretty clever, isn't it?
It really is. It taps into how your inner ear, your cochlea, is naturally organized. There's a structure called the basilar membrane inside.
Yeah.
Think of it like a tiny spiral keyboard. Different spots along this membrane vibrate most strongly to different frequencies. High pitches near the entrance, low pitches deeper inside, near the apex.
Right.
CIs use an electrode array threaded into the cochlea to replicate that. Specific electrodes stimulate specific nerve fibers, essentially mapping frequencies to locations, mimicking that natural process.
It's fascinating technology. And it has a history. It wasn't just invented yesterday.
Not at all. The first ideas and devices emerged back in the late 1950s. But they became much more common and also controversial in the U.S. around the 80s and 90s.
Controversy. Why controversy?
Well, there were a few things. Some advocates in the deaf community raised concerns about autism, this idea that promoting CIs implicitly suggests being hearing is better than being deaf, potentially undervaluing deaf culture and sign language.
I see. That's a complex perspective.
It is. And adding to that, especially early on, the outcomes weren't always dramatic. Some deaf adults went through this significant surgery, the recovery, and the improvement in, say, understanding spoken language wasn't always what they'd hoped for. The tech wasn't as advanced then.
So expectations versus reality, plus these cultural identity issues created tension.
Exactly. But then, moving into the 2000s, there was a noticeable shift. The conversation started to center more on individual choice, on agency.
Right, the person deciding for themselves rather than a purely medical or societal push.
Precisely. Empowering the individual to weigh the pros and cons for their own life.
Okay, so that gives us the foundation. Now let's tackle a huge challenge CI users face. Understanding speech when there's background noise.
Yes. The cocktail party problem, but often much harder, especially with non-stationary noise, sudden clatter, bursts of laughter, unpredictable sounds, not just a steady hum.
That's the real world, isn't it? So how did the technology start addressing this?
Early breakthroughs came from digital signal processing, DSP. A really key development was something called the PICES facility.
PICES?
Yeah, stands for Programmable Interactive System for Cochlear Implant Electrode Stimulation. Quite a mouthful. It was developed at MIT Lincoln Laboratory and installed over at the Mass Eye and Ear Infirmities Research Lab.
Okay, MIT Lincoln Lab, Mass Eye and Ear. Sounds serious. What made PICES special?
Flexibility. That was its superpower. Commercial implants at the time were pretty fixed in how they process sound. PICES was this open platform.
So researchers could tinker.
Exactly. They could try out all sorts of different sound processing strategies, adjust algorithms on the fly interactively. It wasn't just about tweaking existing tech. It was about exploring completely new ways to process sound.
And did it lead to better results?
It did, significantly. New algorithms they developed and tested on PICES showed real improvements in speech understanding for the research subjects compared to the commercial devices they were using. It proved the value of this flexible, research-driven approach.
Let's get into those algorithms a bit. You mentioned early ones like CBank and PBank. What were they doing differently?
Okay, so CBank was essentially a simulation of the older inner-aid stimulator. It did things like automatic gain control AGC to manage volume and dynamic range compression, DRC, basically squashing loud sounds and boosting quiet ones to fit the electrical range. And it used bandpass filters. Key thing, It was configurable for research.
Right, adjustable parameters.
Exactly. Then came PBank, which implemented the CIS algorithm Continuous Interleaved Sampling. This was a step forward.
How so? What did CIS do differently?
Instead of using the whole sound waveform like Interrade did, CIS focused mainly on the sound's envelope. Think of it as just the overall loudness contour, the rise and fall of volume in different frequency bands.
Okay, simplifying the signal in a way.
In a sense, yes. Focusing on what seemed most crucial for speech understanding. It used amplitude-modulated pulses, constant frequency, and interleaved the stimulation across channels to avoid electrical interference.
Now, this is where it got really interesting with subject testing, right?
Yes. This is fascinating. They had one subject, SO4. On a standard consonant recognition test, they scored pretty similarly with CIS 92% versus an Interrade simulation 89%. Objectively, very close.
Okay.
But subjectively, that same person expressed a strong preference for the CIS simulation for just listening to conversation.
Wow. So the numbers didn't tell the whole story.
Not at all. It was this early hint that objective scores aren't everything. The quality of the sound, the subjective experience really mattered. It foreshadowed this shift towards user experience, which becomes huge when we talk about music later.
And there was another finding related to channels.
Right. Also with subject SO4, a 6-channel version of CIS, they scored 99% on that consonant test.
99%.
Yeah, compared to 89% with a 4-channel version. So it strongly suggested that having more channels, more distinct points of stimulation, could really boost performance, more information getting through.
Okay, fast forward a bit. Those were foundational steps. What about more recent advancements in tackling noise?
Well, one really clever approach combines something called Harmonic Structure Estimation with MMSE, Minimum Mean Square Error Processing.
Harmonic Structure, MMSE. Break that down for us.
Okay. Think about voiced speech, like vowels. The sound energy isn't spread evenly. It's concentrated in harmonics, neat, regularly spaced peaks in the frequency spectrum.
Like the overtones on a musical instrument.
Exactly like that. Noise, on the other hand, tends to fill in the gaps between those harmonic peaks, especially that tricky non-stationary noise.
Oh, okay.
So this method first tries to estimate where those speech harmonics are. Once it has a good idea of the harmonic structure, it can basically say, okay, energy at these harmonic frequencies is likely speech, energy between them is likely noise.
So it separates speech and noise more intelligently.
Much more intelligently. It allows the MMSE noise reduction part of the algorithm to work much more effectively because it gets a better, cleaner estimate of the noise, even when the noise itself is changing rapidly.
And the results, does it actually work in practice?
Oh, yeah. The results are quite striking. They tested this in different noise levels, measured by signal-to-noise ratio, SNR.
Right.
At 0 dB SNR, that's really noisy, speech and noise are equally loud. Just using MMSE alone boosted average word recognition scores from maybe 2% to 6%. Not huge.
Okay.
But using the combined harmonic structure estimation plus MMSE, that jumped the average score to 16%.
Wow, from 2% or 6% up to 16%, that's a big leap.
It's a significant improvement in very challenging conditions, and even in slightly less noise. At 5 dB SNR, the combined method took scores from 29% up to 41%. Interestingly, at that level, the MMSE processing on its own actually decreased scores slightly.
So that harmonic estimation part is really crucial.
It seems to make a big difference, especially for understanding speech in those difficult, noisy, real-world situations.
Okay, so we've seen incredible progress on speech, clarity, but music. That's a whole different dimension of sound, isn't it?
Yeah.
Richer, more complex, maybe?
Absolutely. And the experience for CI users with music is, well, it's much more varied than with speech. While things like tempo and rhythm perception can be pretty similar to people with typical hearing,
Right.
perceiving melody, harmony, the timbre or color of instruments that often presents very differently and can be quite challenging.
So the traditional ways of trying to improve music for CI users, what have they been? And why haven't they been a complete solution?
Well, engineers have tried adjusting the device's signal processing or pre-processing the music with algorithms, even tailoring musical compositions. These things can help, but they often operate on flawed assumptions.
Like what?
Like assuming all CI users hear music the same way, which is definitely not true. There's huge variability. Also, assuming the listener is passive, just receiving the sound without wanting much control. And perhaps critically, framing music enjoyment purely as an engineering problem. Optimize a signal, fix the problem.
That sounds familiar.
Yeah.
Like the early speech scores not matching subjective preference, it's missing the human element again.
Precisely. That subjective experience, the joy of music, isn't just about technical specs. This realization led to a really important shift.
Right.
Moving away from just problem solving towards co-exploration, thinking of it as an opportunity for audio engineers and expert CI listeners to work together.
Co-exploration, I like that. Developing tools focused on user agency, on enjoyment, through empathy.
Exactly. And there's a fantastic mixed methods study that really embodies this approach.
Tell us about it. Who was involved?
They brought together 10 professional audio engineers, interestingly, all self-identified as male, average age around 37, working in different music genres.
Okay. And listeners?
10 expert CI listeners, a bit more diverse here. 4 male, 6 female, average age 59, with different types of CIs and hearing histories. And importantly, 7 of them had experience playing musical instruments.
Okay, so experienced listeners, some with musical backgrounds. And the researchers noted the gender imbalance on the engineering side.
Yes, they acknowledged that disparity in AE recruitment in the paper.
So how did this co-exploration actually work? What was the process?
It was pretty involved, not just a one-shot test. It started with surveys and interviews to understand everyone's perspectives. Then they went into cycles of mixing and feedback.
Mixing music.
Yeah, the audio engineers would create mixes of musical pieces. The CI listeners would listen, provide detailed feedback using a special rating system, a modified CI-Mashare scale, basically rating enjoyment from 0 to 100. And the engineers didn't just get feedback from the listeners, they also got feedback from their fellow engineers. And crucially, the engineers used a CI simulator themselves to try and get a sense of what the listeners might be experiencing. Then they'd revise their mixes based on all that input. Iterative refinement.
Wow, that sounds really collaborative.
Yeah.
So what did they learn from the expert CI listeners? What really mattered to them?
A lot of rich detail came out. First off, even before the mixing started, listeners clearly ranked mixes they knew had been informed by CI user feedback higher. They valued that input.
Makes sense.
They talked about how tech changes affected them, things like Bluetooth streaming directly to their processor or using apps to make adjustments. Also, physiological changes, like losing any remaining natural hearing they might have had.
And the sound quality itself?
Oh, yeah. They use descriptions like robotic, tinny, which are common descriptions of CI sound. They also talked about hearing the effects of compression, that squashing of dynamics and noise gating, where quiet sounds might cut out abruptly.
Did they get specific about musical elements?
Very specific. They talked about pitch perception, frequency range. One person mentioned doing better with instruments in the range of male voices, suggesting mid-range clarity was important. They discussed melody, harmony, rhythm. Timbre was huge, wanting sounds less twangy or scratchy, wanting instruments to sound veridical or true to life. Even spatialization, that feeling of 3D sound, came up.
And wasn't there something key about separation?
Absolutely critical. A recurring theme was the need for separation of sonic elements. Being able to distinguish the different instruments or voices clearly.
Like hearing the guitar separate from the piano.
Exactly. Comments like, the separation of the instruments was easy to listen to. It wasn't just about loudness, it was about clarity and definition between the parts. Good balance, clear placement.
That's incredibly valuable feedback.
Yeah.
How did the audio engineers react? Were they receptive? Did their perspective change?
It was complex. Some engineers expressed real anxiety about their own hearing changing over time, potentially affecting their careers. You saw a mix of reactions.
Such as this.
Empathy, definitely. Trying to imagine the CI experience, especially using the simulator, but also sometimes maybe more like sympathy, pity, or sadness about the perceived limitations, which can sometimes stem from assumptions.
Assumptions, like what?
Well, one mentioned was the stereotype that deaf or hard of hearing people just like the bass really blasting, things like that. Preconception.
Right. But did the process itself, the feedback cycles, change their approach?
It seems so, dramatically. Initially, their baseline mixes showed a pretty wide range in how much they considered oral diversity. But after just the first round of feedback from the CI listeners, all 10 engineers rated their consideration of oral diversity as a 5-foot, the top score, meaning considered extremely deeply for all their subsequent mixes.
Wow, so the direct interaction and feedback really raised their awareness and intentionality.
It certainly appears that way, a big shift.
So after all this iteration and feedback, did clear patterns emerge? Were there specific mixing strategies that the CI listeners consistently preferred?
Yes, they identified 2 core strategies that showed up repeatedly in the highly rated mixes.
Okay, what were they?
The first they called essentializing. basically simplifying the mix.
Wow.
By removing or significantly turning down musical elements deemed non-essential, clearing out the clutter. Also, using subtractive EQ, carving out frequencies to reduce spectral complexity, preventing things from sounding too muddy or overwhelming.
Making space.
Exactly. As one of the peer engineers put it, trying to make everything blend together smoothly, cohesion actually seemed to make it worse for CI listeners in many cases. The key was often to essentialize, strip it back to the core components.
Okay, essentialize. What was the second strategy?
Almost the flip side, exaggerating. Once you've identified the essential elements, you make them really stand out.
Boosting them.
Boosting them, yes, through volume increases, but also using tools like compression to make them consistently loud, saturation to add a bit of harmonic richness or edge, boosting EQ in key frequency ranges, even adding octaves like doubling a bass line an octave lower or a melody an octave higher to make it cut through.
So simplify first, then make the important stuff really pop.
That seems to be the pattern, and they found specific techniques associated with this. Things like heavy compression and tight band pass EQ on drums to make them punchy without being messy. Mixing drums and lead vocals quite loud relative to other things. Big boosts in the sub-bass for kick drums and bass guitars. Noticeable boosts in the upper mid-frequencies for vocals to enhance clarity.
Any really creative examples?
Yeah, one mentioned was using long single-tap delays on vocal lines, almost like a creative rearrangement to make the vocals stand out rhythmically and spatially, not just standard mixing moves.
Interesting. So it's not just about technical correction, but creative enhancement tailored to this listening experience.
Precisely. Using the tools of music production in a targeted way, guided by listener feedback.
Beyond the mixing techniques, did this study reveal anything about the sort of bigger picture, systemic issues?
It did. It highlighted feelings of exclusion reported by the CI users within the broader music industry, pointing towards issues of systemic ableism and autism. And on the engineer's side, it revealed that many felt they hadn't really been trained adequately on how to consider oral diversity. And as mentioned, that anxiety around their own hearing preservation was quite prevalent.
So gaps in training and awareness within the industry itself.
Seems that way. And finally, the study strongly reinforced something seen in earlier research. A real desire among many CI users for more agency, more personal control and personalization over how they listen to music.
They don't just want a better signal, they want to shape their own experience.
Exactly. It's about enjoyment, control, and participation, not just reception.
Wow. Okay, what a journey. We've gone from the basic mechanics of how a CI works, through its history, the challenges, the controversies, that vital shift towards individual choice.
Right, then into the nitty-gritty of improving speech understanding, tackling noise with some really clever signal processing like that harmonic estimation technique.
And finally landing on this really nuanced exploration of music. Moving beyond just fixing a problem to this idea of co-exploration, empathy, and user agency in designing for enjoyment.
It really shows how critical thinking and bringing in diverse perspectives, engineers, listeners, researchers, truly enriches our understanding. We saw how focused engineering delivers clearer speech, absolutely. But we also saw how empathy, collaboration, listening to users, that's what's starting to unlock a better music experience centered on agency and joy.
Yeah, it really makes you think, doesn't it?
Yeah.
If getting music and speech right for diverse hearing experiences demands this level of deep collaboration, putting user agency front and center, and being willing to challenge the status quo, what other areas of technology or design or even just how we interact could benefit massively from that same kind of empathetic co-exploration? Where else could we build things that don't just function, but truly facilitate joy and independence for everyone?
Yeah, there is a human in the loop, human in the loop.